but I think it's like potatoes and chicken something, but it's a casserole nonetheless. So we'll go ahead and get started. Maybe. All right, there we go. All right. So again, no pair deck. So just keep that in mind, even though it looks like it on the bottom. So here's the question I pulled. So we're just going to take a minute and let y'all kind of look through it. A student designs an experiment to study the reaction of basically baking soda and vinegar, right? So they give you the equation up top. They put some baking soda, sodium bicarbonate in a flask and add some of the acid, the vinegar. So that's like acetic acid. It bubbles and the flask gets cooler. So I'm going to show you the whole question, then we'll kind of take it apart. So we know it makes bubbles and we know it gets cooler. All right. So A, tell us whether it's an acid-base precipitation or redox reaction. Okay, that sounds like something I can do. All right. Then B, identify the limiting reactant and then justify your answer with calculations. C, the student observes the bubbling is rapid at the beginning and then gets slower. Explain this change in reaction rate. So I'm already thinking like maybe kinetics, right? And then part D, in thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. So I'm assuming that most everybody has seen both enthalpy and entropy in terms of delta G. If you haven't got that far, if you haven't got to unit 9, that's okay. We'll kind of walk you through as you go. All right, and then, so let's just look at just the parts that we want to worry about just this moment. So identify the reaction represented above as an acid-base reaction, precip or redox. Justify your answer. So if we look at the equation, no precipitate is made. I don't see a single solid on the right-hand side. So that means that it can't be a precipitation reaction. That would have been way too easy. All right, so what else do we know? In an acid-base reaction, one thing has a hydrogen that it donates, and another thing accepts a hydrogen ion. So that's how we would know if it was a acid-base reaction. So do we see that? Well, let's look. So the HC2H3O2 is losing an H, and it's becoming NaC2H3O2. So it looks like double replacement to me. But let's see. Yeah, I think we kind of have this. I think the HC2H3O2 is donating the H, and the HCO3, the bicarbonate ion, is accepting the H. So I think this may be an acid-base reaction. A redox reaction, we'd be assigning oxidation numbers. So we would have to go back to what you learned in Unit 4 about what is a redox reaction. So redox reactions are ones where one thing gains electrons and one thing loses electrons. And losing electrons is oxidation, and gaining electrons is reduction. But so we'd have to assign oxidation numbers. There's a lot of elements up there. So if we wanted to take the time, we could, right? So the oxygen would be -2 everywhere. The hydrogen would be +1 everywhere. The sodium would be +1. You know what? I think just for the sake of, let's keep it easy, it really does look like an acid-base reaction because one thing is giving up the H and the other thing is accepting the H. So I'm going to stick with that. So I would probably say it's acid-base because one thing is donating a hydrogen, one thing is accepting the hydrogen. So that's my justification. So, all right. Ooh, B, identify limiting reactant. Ooh, and justify with calculations. So identify, keep in mind, identify just means say it. So it's either the baking soda or it's the vinegar. So it's either the bicarbonate, sodium bicarbonate, or it's the acetic acid. So you were probably taught many ways to find limiting reactants. One way to find limiting reactants is to start with what you're given, right? 2.24 grams of sodium bicarbonate, and go to moles using the periodic table and the molar mass, and then use the balanced equation to go from moles of the bicarbonate to moles of a product, say like carbon dioxide, and then change it to grams. So kind of like the stuff you did in like chemistry 1, right? So we could take the amount of given and go to a product, and then we could do the same thing for the acetic acid, right? So change, we know the milliliters and we know the molarity, right? So we can find moles of the acetic acid, and we can just go from moles of acetic acid to grams of CO2. That's one way of doing it. Seems kind of long, right? But it's one way to do it. So if you wanted to pick a product and go from grams of bicarbonate to grams of CO2, and go from the milliliters of the acetic acid to grams of CO2, whichever answer is smaller, that is the limiting reactant, right? That's one way to do it. Another way is change each one to moles. The first one using the molar mass in the periodic table. The second one using the milliliters and the molarity. And then because the equation is a 1-to-1 ratio, whichever number of moles is smaller is going to be the limiting reactant. So remember that limiting reactant is the thing that you're going to run out of, right? So the stoichiometry says, I'm going to use up all of this chemical reactant. So this is easier because the equation is balanced with nothing but ones, right? So I would say, who is the limiting reactant? That would be the sodium bicarbonate. And the reason why is the math that's in front of you. You could either do it the way that is shown in black on the screen, or the math that you would have done to do the steps in blue. Whichever way you would have done it, you could have found out who is limiting with justification there. Lots of different ways to get there. All right, now, the student observes that, and I really should have formatted this differently because it keeps showing up. The bubbling is rapid at the beginning and then slows down. Explain this change in the reaction rate in terms of collisions between reactant particles. All right, so let's see. Let's review kinetics real quick. We know for a chemical reaction to occur, particles have to collide, and they have to collide with each other with enough energy, and they have to collide in the correct orientation. So they're talking about collisions between particles. So we need to make sure we're figuring out what we know about how reactions occur in kinetics. We know that the greater the number of particles, the more collisions occur, right? So if you increase the amount of reactant, then typically you'll get a faster rate of reaction. That's because there's more particles causing more collisions. So this is just a review of kinetics. We also know that temperature can affect rate of reaction, right? So the warmer it is, the particles are going faster, and so they're going to run into each other faster, right? Or more frequently. So if the particles are increasing in temperature, that means they're going faster. And if they're going faster, you're going to get more frequent collisions, right? And they're also going to hit with more energy. So increasing the temperature, we can think about, oh yeah, when they hit with more energy, it might be enough energy to overcome the activation energy, right? So these are things we just know. If particles are in the wrong orientation, no reaction will occur. So let's figure out what in all this green stuff will help us actually answer the question, right? So they don't say anything about the temperature changing. It said it got cooler before, but it doesn't say to do that in terms of the temperature of the particles. So maybe we want to talk about that. I don't know. But they said, as the reaction continues, it gradually slows. So we got to kind of give it some thought. So what in all this green stuff will help us? So basically we know that, I got a direct message from somebody about the Pear Deck. I am sorry, we are not doing Pear Deck tonight, only because I can't get the animations to show up in Pear Deck. So even though it says students write your response, we're not going to do that tonight. So I apologize. I'll make sure I fix it for next time. So what's happening is we add the baking soda and vinegar. Why would it get slower? Well, I know temperature matters and I know the number of particles matters. So let's think about, they've already asked us to do limiting reactant. So they've already pointed us to say, hey, you're running out of reactants. So let's think about that. As the reactant particles disappear and turn into product particles, there are fewer and fewer particles of reactants. So if there are fewer and fewer particles of reactants, then you're going to see fewer collisions. So I really think what they're looking here is not about temperature, although I guess we could talk about that. I think they're really saying that as the reactants get used up, that there are fewer and fewer collisions because there are fewer particles to run into each other. I think that would probably be our approach. I'm going to show you all the answers to this later, but just try to think if that makes sense to you. Then we go to this part, all about thermodynamics. Now, you have all hopefully seen enthalpy, delta H, right? In Unit 9, we also get into entropy, and we also get into delta G. So just in case you don't know, entropy is the amount of chaos or disorder in a system. And enthalpy is, remember, the change in energy. So nature loves a delta H that is negative, so exothermic things, and nature loves an increase in entropy. So anytime we have a reaction that is exothermic and is a reaction that increases entropy, then we know that's something the world, the universe really wants, right? So these are always going to be what we call thermodynamically favorable, right? So we have to think about, what do we know though? It says the flask gets cooler. Now, gets cooler means it's endothermic. Now, this means that it's not the delta H part. Delta H, it has to be negative. That makes it thermodynamically favorable. But in this case, we know it's endothermic because it gets cooler. So that means that the enthalpy only is out, and the both enthalpy and entropy are out. So it's probably just entropy. But let's talk about, how do we know if it's more entropy or less entropy? Well, you have to remember that entropy is disorder, right? So let's look at the states of matter. So on the left-hand side of the equation, you've got a solid, and you're mixing it together with an aqueous solution, right? And then on the right-hand side, the products, you've got an aqueous solution and water and a gas. Because remember, the question said there were bubbles. So we're looking for those word clues. So when you take the AP exam, don't forget to break out your pencil and circle things and go, oh yeah, this is bubbles, this gets cooler, those kinds of things. So I know anytime I've got a solid changing into a gas, gases have much more entropy or disorder than solids do, because the gases are bubbling out and they're flying all over the room and stuff. And a solid tends to be very ordered, very low entropy, right? So that means that I'm going to circle entropy only, right? That's what I'm going to circle, is entropy only, right? And then justify your selection. It could be all kinds of things, right? So what does delta G have to do with anything? Well, delta G is a fancy thing called Gibbs free energy. Here's what that means. When delta G is at 0, then you're at something we call equilibrium. The forward reaction isn't favored. The reverse reaction isn't favored. Both reactions are equally favored. That's at 0. So when delta G is negative, that means that a reaction is thermodynamically favorable, or back in the day, we would call it spontaneous. It just means nature's okay with it happening without you having to put in a lot of energy or something like that to force it to happen. So fire is very exothermic because, very thermodynamically favorable because it has a negative delta H, it gets hot, and you're turning that fuel from the fire, you're turning it into a bunch of gas molecules. So things that are that have a negative delta G are thermodynamically favorable. That's what's driving this. So you could do it mathematically. You could dump in a positive number for delta H and show that if delta S is big enough, a positive delta S, that the positive delta S can kind of overcome the positive H because it's delta H minus T delta S. Or you can also say that, in order for it to be negative delta G, it either has to always be negative delta H and positive delta S, or that when delta H is positive, that the delta S has to be positive as well to increase the entropy. So you can do it mathematically. You can also try to describe your way out of it, but there's no numbers given to us. So I don't think we really need to worry about a calculation. All right, so here's the rest of the question. I'm sure y'all were like, wait, weren't we just looking at the question? This is like from 2016. This is a really long free response question. We're looking at like 10 points here, right? So that's what we want to look at. So the 8CO3 ion has 3 carbon to oxygen bonds. 2 of them have the same length, and the third carbon to oxygen bond is longer than the other 2. The hydrogen is bonded to one of the oxygen atoms. Draw a Lewis electron dot diagram or diagrams for the bicarbonate ion that is consistent with the given information. I was going to have y'all draw this on Pear Deck, but again, my animations weren't working, so my bad. All right, so let's think, why is it telling us about the bond length? Like, what would we do to think about why they're going out of their way to tell us something, right? I just have to figure out what they're saying. Okay. So 3 carbon to oxygen bond. So I think I would probably drop carbon in the middle and then have oxygen around it, right? So 1, 2, 3, and because it says there's 3 carbon oxygen bonds. So carbon in the middle, oxygen, oxygen, oxygen. All right. It says 2 of them are the same length and the third one is longer than the other 2. So what do we know about bond length? Well, they're all the same bond. They're all carbon oxygen. So let's see. What do we know? Single bonds have the least amount of bond energy and are the longest, right? Double bonds are shorter and have more energy, and triple bonds are the shortest. So I would go ahead and take a minute and draw out on paper, what do you think the Lewis structure for this would be? And I'll show you what the answer is here in a little bit, but kind of think through the question. I know carbon goes in the middle with 3 oxygens around it, and then hook one of the hydrogen, or hook the hydrogen to one of the oxygens. So go ahead, remember it's an ion. So remember when you're doing Lewis diagrams, since it's a negative ion, that's going to give you an extra electron. So I'll give you a minute, go ahead and draw out the electron dot structure for it. Hey, Mr. Matt, I just realized, did you ever hit record?
You
did?
did?
Okay.
It's recorded.
Okay. I meant to remind you when I started. I was like, oh, well, okay.
I missed about the first 2 or 3 minutes, but I got it when you started the content, so we're good.
Okay, that's good. That's right. Okay. Probably would have remembered about 8 o'clock, you know. Oops.
Yeah, I'm lucky that I remembered.
Now, as you're drawing your Lewis structure, go ahead and make sure that you think about 2 of them are shorter and 1 of them is longer. So maybe 2 of them need to be double or triple bonds, and 1 needs to be like a single bond because that would make it longer. Maybe something like that. I'll give y'all like another 30 seconds to work through that. All right, so hopefully you've got that written out. Surely this has to be the end of the question, right? There can't be anything else. No, there's one more thing. This is the last one though, that's good. All right, so a student prepares a solution with equal amounts of the acid and sodium acetate. The pH of the solution is measured to be 4.7. The student adds 2 drops of HNO3 and stirs it, observing that the pH remains at 4. All right, so here's what I'm getting. I think this is a buffer question because I know when you have an acid, like acetic acid, and its conjugate sodium acetate, I know that's a buffer, right? And it says equal amounts, so that's good because that helps me. So this is, I think, a buffer problem. All right. The student adds 2 drops of 3.0 and stirs the sample, and the pH remains the same. Yeah, okay. This is definitely a buffer because when you add an acid to a buffer, the pH remains pretty much constant, right? Write a balanced net ionic equation. Well, okay. It's not really a buffer question. They just need you to understand how to write a balanced equation. Okay, well, I can do this. All right, so let's think about this for a minute. HNO3 is a strong acid. How do you know it's a strong acid? Because it's one of your strong acids. You got Hickel, Hibber, high, HCl, HBr, and HI, strong acids. And then you got a couple like nitric, this one, HNO3, H2SO4, also very strong, perchloric and chloric, strong acids. So when we write net ionics with strong acids, we separate them into ions. So we want to make sure that we write that as H ions and NO3 ions, right? Okay. Weak acids are kept together. So do we have any weak acids? Maybe we do. And okay, all right, let's keep going. The HNO3 will react with the basic portion of the buffer. So our buffer is HC2H3O2 and NaC2H3O2. I know the acid is the one that starts with H. So I know it's not that. That means the strong acid, the nitric acid, will be reacting with the sodium acetate. Now, in the equation, it tells you the sodium acetate is aqueous. So we know it's soluble. So anything with sodium is soluble, right? Group 1 things, nitrates are all soluble, right? So anytime we have a soluble salt like sodium acetate, we want to split it into ions as well. So we're going to split apart the nitric acid. We're going to split apart the sodium acetate. And this is the equation I got. So you got the hydrogens and the nitrates, right? and the sodiums and the acetates. That's all on the reactant side. And then over on the right-hand side, because it's like double replacement, right? So over on the right-hand side, that's the reason why I left the C2H3O2 together is I know that it's a weak acid. And I know you're like, wait, how do you know it's a weak acid? Because it ain't strong. If it ain't one of the strong ones, then it's got to be a weak acid. So when that acetate, the C2H3O2 negative ion, grabs onto the hydrogen, that means that it's going to stick to it and stay stuck to it. We don't want to separate those. That's only strong acids, not weak. But we do want to split apart the sodium ion and the nitrate ion because, again, those are going to be soluble things, right? So this is what we call our complete ionic equation. So now to do a net ionic equation, we want to look for spectators. And spectators are the things that are exactly the same on the left and the right-hand side of the equation. So if this was pair deck, I would have y'all actually cross them out. That was my plan, but you know, best laid plans and all that kind of thing. So what do we see that's exactly the same? All right, so I got a nitrate on the left and a nitrate on the right. So I think I can get rid of those. Those are out the door. Those are spectators. I also have a sodium ion and a sodium ion. So those two, I would also get rid of that. Those are spectators. So I think my net ionic equation is going to be the H plus, we'll keep that, the acetate, C2H3O2, and it makes HC2H3O2. Now, notice I'm not using states of matter because typically when they ask you to do this on the AP exam, the only time you would have to do that if it was like a precipitate, right? So unless they tell us to specifically write down states of matter, that's not something I'm really worried about. Okay, so that's the last part. So let me back up a little bit. Right. All right. So what I want y'all to think about is here's part of the question. How many points do you think that first one should be? I think maybe just one because it says identify, right? And then part B, based on the information, identify limiting reactant, justify with calculations. I don't know, one, maybe two there. Maybe they're being generous there, right? The bubbling is rapid. Explain that. One or two, I don't know. Circle the one that drives it forward. That's got to be just 1 point because you're just circling something. Justify in terms of delta G, maybe one or two because it sounds mathy, maybe just one. I don't know. Right, let's look at the rest of the question. Let's see. Okay, and then the Lewis structure, maybe one or two, maybe 2 points, maybe 2 points. We'll see, right? And then the last part, write a balanced net ionic equation. I'm guessing just one, right? Because this whole thing is going to be worth 10 points. So what I want you to think about is if I gave you this question today, how many points do you think you could earn? So I was going to actually have y'all add that up. So, you know, how many points do you think you could earn? So let's look at the real rubric. So you had to say acid base. You got 1 point just for saying acid base. Y'all, you got pick one. You know it's not precipitation. There ain't no solid. And really one thing was given up an H. That's an easy point. That's an easy one. I get 1 point just for saying acid base. 1 point for some kind of a justification. So they said no solid precipitates and none of the oxidation numbers changed. But I think you could also get away with saying, I know an acid base is when one thing gives up an H and another thing takes the H. You can get away with that, right? And then this part B, 2 points. You got 1 point just for finding the number of moles. When in doubt, mole it out. If you're given grams, find moles. you're given milliliters or something and it's asking for limiting reactants, find moles. And then you get 1 point for identifying it consistent with your calculations. You know what that means, y'all? Even if you screwed up your calculations, right? You're like, oh, I just can't math today. As long as you wrote down the number of moles and then you based your answer on that number of moles, boom, you would have got the point. So let's say on that on part B, where they changed 60 milliliters times 0.875, what if instead of 1,000 milliliters, you thought that a liter was 100 milliliters? Let's say you did that. And so you got that the moles was 0.525, not 0.05. Let's say you got 0.525. And then you could have made some decision. So as long as you're basing your decision on the number of moles, you would get that second point. Now, if you did the math wrong, you wouldn't get the first point, but you could get the second point as long as you're basing your, that's 4 points, y'all. 4 points on a 10-point question. As the reaction proceeds, both reactants are consumed. That's right, because that's what we said. They're going away and their concentrations go down. I didn't say concentrations, but I think if I said there are fewer and fewer particles, I think that still would have counted. Collisions become less likely as their concentrations decrease. Well, I said that. I said the fewer the particles are, the fewer collisions there would be. I think I earned that 1 point. Me personally, I think I earned 2 points because I did such a great job. So now we're up to 5, right? Consider that the flask gets cooler. What drives the chemical reaction? You get 1 point for circling entropy. Now, let me just tell y'all. One of my students in 2016, when they answered this question, said that they missed this because they didn't circle anything. And I'm like, look, there's 2 possible ways to get this wrong automatically. Don't circle anything and circle everything. So it says draw a circle around one of the choices. So one of my students said, what if you drew one great big circle around all 3 choices? And I was like, no, you can only draw the circle around one of the choices. So you get 1 point for entropy. So now we're up to like 6 points. All right. You get 1 point for saying that it's favorable when delta G is negative and delta H is positive because it got cooler, and that delta S is positive because you're making a gas. So basically, I nailed this. I didn't have to do a calculation, but as long as you're saying that entropy, because it's making a gas, that makes it thermodynamically favorable and delta H is positive, you would get that point. Now, me personally, that's a lot of words for 1 point. I think maybe I would probably give myself 2 if I was handing out points. You get 1 point for a correct Lewis structure. And you get 1 point for indicating resonance. Resonance, wait a minute. How was I supposed to know to draw 2 of them? Well, let's look at the question again. It says, draw a Lewis electron dot diagram or diagrams. Oh, okay. I should have read that more closely. I should have thought maybe I should be drawing more than 1. So if you drew a resonance structure, good for you, right? Good for you, good for you, good for you. Then what was that longer, shorter thing going on? What was that all about? Well, turns out that hydrogen attached is going to change the length of the bond between the carbon and the oxygen. And then you got to remember that you've got a single bond and a double bond that moves around. So really, that bond as it moves around really makes each bond like 1.5. That's why there's 1 longer and 2 shorter. So, all right. So I wasn't great on that, but I tell you what, I can draw a Lewis structure and I think I can get this point. Now, how many of y'all included brackets? You gotta remember the brackets, right? So if you included the brackets and showed it as negative and drew a good Lewis structure, all it says is a correct Lewis structure, by the way, then boom, you would have gotten a point. And then if you remembered that your wonderful teachers like Mr. Ballinger and Miss Dasinger have been telling y'all to don't forget the resonance structures, then boom, you could have got a second point. But you know what? I've already gotten so many points so far that I don't even need this point, even if I got it wrong. This is like 9 points so far. All right. So 2 points for the structure. I can live with that. All right. And then it says, draw a net ionic. So you could have either represented the bottom one. That's kind of what I said, right? The acetate plus the hydrogen ion makes it. Or if you're fancy and bougie, maybe you made the hydrogen ion a hydronium ion, the H3O. Maybe that's what you did. Either one is okay. Either equation would be acceptable and you would get 1 point. So here's my thing. For this question right here, this was question number 2. So in 2016, question number 2 had an average or mean of 4.39. 4.39 out of 10. What was the average score on the AP exam? A 3, a passing score. So can you get 4.39? Well, just as a reminder, let me go back real quick. Oops, too far. You get 1 point or 2 points for part A. You get 2 points for part B. Boom. Look at that. You got 4 points. All you need to do is pick up one more and you're beating the average. You could pick it up on kinetics. You could pick it up by circling entropy. You can pick it up in the justification. You can pick up 2 if you're good at Lewis structures, and you could pick up 1 for writing a net ionic. Y'all, if you can't beat the mean here, there's just something wrong with you, right? So I thought this was a good long one from 2016. All right, so I know that took a while. Holy cow, it's 40 minutes. All right, let's look at a short one. All right. At high temperatures, this compound reacts according to the equation above. Okay. The rate of the reaction was studied. Rate of the reaction, another kinetics question. 2 different trials, each with a different starting concentration, were carried out. The data were plotted in 3 different ways as shown below. I'll show you a second. I just want to show you part A. For trial 1, calculate the initial pressure in atmospheres in the vessel. Pressure, wait, I can do pressure because I know PV equals nRT. I know the ideal gas law. All right, R is the gas constant. Now remember, this is on your sheet with all the stuff. So you want to pick the one for atmospheres because it says in atmospheres. The temperature is 625 Kelvin. They didn't even give it to you in Celsius. You can just plug that sucker directly in. The tricky part is, what are you doing for moles and the liters? So let me show you the graph. So the graph showed us the molarity versus time. Now, molarity is at moles per liter. So first of all, we need to pick out, are we looking at the black dots on the graph, or are we looking at the open circles? And the open circles are trial 1, and the black dots are trial 2. So let me go back and read the question because I think that was in there. For trial 1, calculate the initial pressure. So initial pressure would be at time 0. Okay. So the initial concentration for trial 1 was 0.020. So if you wanted to screw this up, you could totally pick 0.010. You could pick trial 2. So don't do that, right? And then all we have to do is plug in everything because it's 0.02 moles and 1 liter. So if I plugged everything in, I'm going to get the answer of 1 atmosphere. So that's a math question. We get a calculator. Everything should be good. All right, I can do that. Use the data plotted in the graph. So this is part B. This is a short question, by the way. This is only 4 points. Determine the order of the reaction with respect to C4H6. Oh, Lord. It's been so long since I did kinetics. But I remember my teacher telling me to find the graph with the straight line. And the only graph that, well, the one on the lower left looks kind of straight, but not near as straight as that one on the right. So the one on the right to me looks like, yeah. That straight line, that means that's the one that's telling me what the order is. I just need to remember my integrated rate laws. I wish I had a reference sheet. Well, if you look on your reference sheet under kinetics, they only give you 2 integrated rate laws. The first one is ln, and that's the first one, so that's first order. The second one is 1 over the concentration, and since it's the second one, that means it's second order. So I'm going to say second order because 1 over the concentration versus time, that's what tells me 1 over the concentration tells me it's second order, right? Now, here's the funny part. The year this came out, one of my students had absolutely no idea how to do this, right? So the student numbered the graphs. This one would come first, and then I would make this other graph, this one would come second, and then this graph would be third, because they were determining the order of the reaction with respect to C4H6. So they actually took the graphs and said, I would use this graph and then this graph and then this graph. And I just shook my head because I was like, I knew I taught that person more than that. So it is the one on the right. All right. The initial rate is 0.0010 moles. Calculate the rate constant. Right, so how do we write a rate law? Rate is equal to K times the reactant raised to some power. Rate is equal to K times the reactant raised to some power. So we know the power is 2 because you already said it was second order. So the rate, they tell us, is 0.0010. I can plug that in for rate. I know the initial concentration for trial 1 is 0.020. So if I plug in my rate they give me, and if I plug in the initial concentration they give me, I can actually solve for K. And there's the math. I can do that. I can do that with a calculator, right? So 0.0010 divided by 0.02 squared. And we get the answer 2.5. All right, so far so good. I think there's one more part because this is just part C, right? All right, let's see. For trial 1, calculate, we've already gone through all the parts. Calculate the initial pressure in atmospheres. 1 point just for the correct setup, y'all. 1 point just for plugging stuff into PV equals nRT. 1 point just for reading a graph and knowing that it's 0.02 moles in 1 liter. 1 point for the setup, 1 point for the correct answer. That's 2 points, y'all. That's 2 points, not even from AP Chem. That's 2 points just from Chem 1. And I'm not talking honors or pre-AP either. I'm just talking about plugging in to the ideal gas law. Now, part B, all you had to say is second order. Notice that it doesn't say justify or explain because you don't have to. It said determine the order. If this was a longer question, like one of the 10-pointers, they would probably like justify your answer. But just if you say second order, boom, you get the point, right? Good job. All right. Okay, hang on. That's not me. I clicked on something wrong. All right. Okay. So this was question 5. So this thing, the average was 2.08 points. So just 2 points out of 4. Wait a minute. Let's see. Sorry, that's me. 2 points just for doing perfect. I can do that. You get 1 point just for saying second order, y'all. Come on. You can get that point. What was the Next part of the question. I'm missing one part of the question because that's only 3 points. Oh, calculate the rate constant. That was the 4th point. I forgot to throw that in the rubric. You get 1 point for doing the math right and getting 2.5. I don't think you even had to have the units there with it, but you always should do units because that's what teachers tell you to do, right? So that's the 4th point. So y'all, if you can't beat the average, if you can't beat 2.08, come on, what's wrong with you, right? So those are the 2 FRQs that I looked at, and I did want to take a moment and go ahead and look at some of the multiple choice. So Matt, this is on you. All right, so this is also from 2016. So